All right, so we're very excited to have Samuel Ainsworth present to us today. He's a senior research scientist at Cruise AI Research, where he studies imitation learning, robustness, and efficiency. He completed his undergraduate degree in CS at Brown University and received his PhD from the University of Washington. His research interests span reinforcement learning, deep learning, programming languages, and drug discovery. He's previously worked on recommender systems, Bayesian optimization, and variational inference at organizations such as the New York Times and Google. And Ray, we're very excited to have you give us a talk about your very highly rated paper, Git ReBasin. So over to you.
Well, thank you, Purva, and thank you, Carl, and everyone for having me. It's really an honor to be here, so thank you so much. I'd like to do something perhaps a little less unconventional and do a concurrent demo. So, at the risk of demoing, can I get a volunteer from the audience? Okay. So Mia, I think, did I spell that right?
Sure.
Okay. Mia, what is your favorite flavor of ice cream?
Tiramisu.
Okay. Okay. Can I get another volunteer from the audience? Sachet. Okay. And Sachet, what is your favorite thing to do on the weekend?
Ooh, stand-up comedy.
Okay, stand-up comedy. Okay, and can I get a third volunteer from the audience?
Basil, like Basil would be at the end.
Okay, like that?
Yeah, sure.
Wait, sorry, no.
It's Basil and ILE.
ILE.
Yeah, exactly.
Oh, got it. Okay, and Basil, what is your social security number? No, I'm just kidding. We're hashing it anyway, so who would ever know? No. Let's say, where is your favorite place to vacation? Thailand? Okay, Thailand. Okay, so I have here, it's a quick collab notebook. So we'll install a few things, and then now I have random seeds for each of you. So I'll let this cook. It's going to install a few dependencies, and then we will come back to it shortly. Okay, great. So yeah, I'm here to talk today about Git ReBasin. This is a project that I was working on for a few years and put out a few months ago. So if you're anything like me, when you think of deep learning and you think of lost landscapes, you hear the non-convex refrain, and you think of a function that maybe looks something like this, something that you'd see in your sort of introductory textbook on non-convex optimization. But what I'd like to argue for you today is that this is actually not the right mental model to have. And in fact, something that looks a bit more like this is more appropriate. So this is showing an actual lost landscape for a real neural network. And if there's one sort of slide to capture the whole presentation, this is it. So here's the idea. I'll train my model, let's say model A, and I reach some point here in weight space. And let's say independently, Roshi trains his model, model B. Let's say same data, same general kind of model architecture, but different computer, different random seed, different machine learning framework, different everything. And Roshi lands at model B, right over here. And if we just sort of interpolate between A and B, that doesn't do anything useful, right? So we end up going to bad places in our lost landscape. And the whole sort of point of our work is that we can be a little bit clever. And let's say I take Roshi's model B and I just permute units in model B. I'll be more specific about that in a moment. But in particular, I'm not changing the functionality of the model at all. So for all inputs, same outputs. And I permute it to just be closer to model A, to my model. And then once you do that, suddenly you can actually interpolate and you can get nice behavior. So that's the whole, that's going to be the central story. And also I should say, feel free to interrupt me at any time with questions. I'm happy to take questions. I love to be interactive. So. Okay, so there were a few phenomena that were weird to me, and I think still are sort of interesting and unusual. So number one, why does SGD work in deep learning, but it doesn't work everywhere, right? So I was coming before this from doing policy learning stuff. In policy learning, SGD works okay-ish sometimes, but it'll also totally fail. And that's not something that, you know, happens in vision that often, right? Like you throw SGD at your model, you get a big computer, and then it just works, right? Number two, we're all the local minima. So, you know, if I train my model on some data set and I get accuracy, you know, 60%, and then Carl trains the same model and Carl gets accuracy 97% because he's a professor, right? That we would all be like, that's a little bit, you had all the same hyperparameters, you did everything the same. That's a little bit sus, right? If I was an advisor, I'd be like, okay, you know, let's try again. And number three, if we take, you know, the same model, the same data, and we train with different initializations, different batch orders, different everything, why do they have the same dynamics, sort of training dynamics? What I mean here is like, if we just plot the loss curves, if I have seed A and seed B, they look basically the same. There's some noise, but like you're following the same sort of general trajectory down your loss landscape. And that's, to me, a little bit odd, right? If this is genuinely non-convex, why are we not seeing some more sort of interesting and varied behavior here? All right, so here's a hypothesis. Maybe permutation symmetries in our models are to blame for this. So if I take a model, right, and let's say I train a model and, you know, unit, I have a hidden layer here. So this is maybe my input and then the rest of my model. This maybe is a hidden unit that represents, you know, let's say cats, and unit 3 represents dogs. But the numbers 1 and 3 are not relevant or important in any way. So I can just swap them. Like you could train your model and you could get dogs in unit 1 and cats in unit 3. It's the same thing. As long as I'm moving my weights around, the order of things in hidden layers doesn't matter, right? So, okay, swap the hidden units, same model, same function, but different points in weight space. So just to give a quick sense of how big this problem might be, if you take a ResNet 50, you get 10 to the 55,000 permutation symmetries. And that's a big number. And the scale of big numbers, the number of atoms in the universe is upper bounded by 10 to the 82, right? So we're talking about a lot of redundancy in weight space. And if you just think about like, you know, I have some hypercube, like, where is this all going, right? Where are all these points? You just sphere pack it all in there. You have to replicate these things a bunch of times. And so this is a conjecture that came from Entezari et al. For the first time. So also check out their work as well. Okay, so if I train my model and Roshi trains his model, and here we are, the goal is going to be, you know, okay, well, first of all, if we just interpolate, then we can create a plot that looks like this up top. So I have theta A over here, I have theta B over here, and I can just linearly interpolate between them in weight space, right? So I walk this way, and I can plot what the loss looks like along that path. And I'm going to call this difference, this size of this bump, the barrier, right? This is coming from great linear mode connectivity work from Jonathan Frankel and others, right? And so the name of the game is going to be, okay, that's great, but can I pick a different equivalent point in weight space, the same function, but a different point, pi of Roshi's model, such that suddenly we're closer. And then once I interpolate, I get something that's has much lower barrier. Ideally, maybe even is convex or flat. And these are in a circle because if you think about it, they all lie on some hypersphere, right? They're all kind of, you don't change the norms, right? And okay, that's great in theory, but the million-dollar question is how do we find pi, right? As I've said, there's a gajillion of these things, so how do we pick one? It's a needle in a haystack type of type of problem. Any questions before I go from here?
What are some examples of data A exactly? Like, is it just some other like set of ways that, like, why would you want to interpret, for example? And what is,
Oh.
or could data A be like the global solutions? Or
Yeah, great question. Great question. Like, why should we care? Like, what's the, for what purpose? I would say there's a few reasons. One is scientific, right? So I'm going to argue that actually a lot of loss landscapes are sort of practically convex modulo permutation symmetries, which is perhaps interesting just in terms of our understanding of the geometry of what's happening. But okay, you know, you want to build things, like what good is it? I would say that it's interesting in a few different places. One is federated learning. So you train your model, I train my model, and we want to safely incorporate our models together, right? Another is you can think of a lot of state-of-the-art results now are now coming out of like ensembles of multiple things getting like model soups, right? And sort of just average a bunch of things and stuff works. And this is another way of doing stuff like that. So hopefully this is something that you can also use practically. I'll have some results coming up. It's a good segue for other stuff. Yeah. Great question. Yeah. All right. So before I hop into this, actually, let's hop back into our thing here. And okay, here we have your seeds. Okay, so we've got Mia, Sachit, and Basil. I hope I'm saying that right. Okay, okay. And so here are your seeds. So now what I'm going to do is we're going to train a small model. So this is going to be an MLP on MNIST, just for the sake of the time that we have here. So I'm going to set up a training loop, and then we're going to train 3 models. And each model, their random seed is going to be set with your random seeds. So this is your card. Everyone memorize your card. And the random seed is going to determine the initialization and the batch order, right? So as much as possible, it's going to be randomized. So, okay, let's set that out. Okay, and then first things first, let's talk about these different methods. So in the paper, we talk about 3 different methods sort of increasing complexity, or one building off the other. So the first one is activation matching. So this is actually like, it's a very simple idea, right? The idea is, well, let's just look at what's happening in these units, in these networks, and match them, right? If I look at a unit and this unit always fires when you look at dogs, and if you have a model and your unit always fires when you look at dogs, then those are dog units and we should associate them, right? So very simple algorithm. I'll just take my whole data set, I'll run it through my model A. Let's say this is layer 5. I run it through model A and I record the activations for every unit in layer 5 for every data point. So I have n data points and I have some number of activations. And I do this for model A, I do it for model B. And then the idea is, okay, I want to find some association, some one-to-one matching between these things. And how do I want to do it? Well, okay, one thing that might make sense is let's do a least squares matching. So I want to find some things such that I permute them, and then I look at the difference in least squares and it's minimized. So you can push through the math. Don't worry about the equations so much as seeing that it nicely results into something that looks like this. Let me move this around so you can see it perhaps a bit better. And
Sam, if you had the
thank you. Learn something every day. This is why they pay you the big bucks. Okay. So the nice thing here is that this reduces to something convenient. This is actually a linear assignment problem. There we go. So what is a linear assignment problem? Don't worry too much about the details, but it's just, I want to match some number of, let's say, workers to jobs, and I want to do it one-to-one, and some person has some cost for each job, right? And that's exactly what's happening here. So I'm taking the maximum over P, the set of permutations of some sort of Frobenius solution. And the nice thing about linear center problems is that we can solve them, right? We can solve them in polynomial time. You can just go into SciPy and run code and it just works, right? So it's fast, it's easy. Yeah.
So this is for like every layer crossing, basically. So you need to do this separately for each of them and then string them together somehow.
Yes, that's right. And but one nice aspect about this, which we're not going to have for the rest of the algorithms, is that I can do each layer independently, right?
And
So
just, like multiply through the permutation.
exactly, yeah. So then, yeah, right. So in terms of when you want to go apply this, you're going to have to multiply your, let's say you have some weight matrix here, you have to multiply left and right.
Yeah.
Yeah, great question. Yeah. So yeah, this is nice. We can divide and conquer across all of our layers. The optimization problem at layer 5 doesn't affect the optimization at layer 6, so it's very easy. And it's kind of intuitive as well, right? We just sort of look at our activations and we try to match them as best as possible. Next up, weight matching. So weight matching is another idea. Let's say that I have, let's say I train a convnet right in my model, and let's just think about the first layer. Let's say I have some filter in my first layer that kind of looks like this. So I can say, okay, that's like an edge filter, right? For something at this angle. And Roshi trained his model, and he also has filter that looks like that. And I can say, okay, those two look similar, so they should be associated, right? So we can just look at the weights and say similar weights should line up. So here's a different idea. Let's ignore the data and let's just look at the weights. And we can think about just aligning the weights of our two models. So one idea is you can minimize L2, you can maximize inner product. It's the same optimization problem. And again, don't worry too much about the details of the math, except to notice that here I have a linear assignment problem. Here I have a linear assignment problem. But here I have something actually a little bit different, right? Here I have P1 and P2 in the same sort of norm. And this actually is a lot trickier. So here I'm permuting just rows or just columns. Here I'm permuting both at the same time. And it turns out that this is hard. So in fact, we proved that this is NP hard. Yeah.
So do you need to assume that there's a one-to-one matching between the two network? Possibly one model like missing one component, the other one.
This is a good question. Yeah, and there's other work arguing that, like, yeah, some models don't have components that line up at all. So like, what do you do? Like there's this great conversion learning paper and so forth. It doesn't seem to be an issue for us. Like, and why that is kind of interesting. I'm not entirely sure. But I think one argument that I'll make is that basins can actually contain a lot of stuff. So like, you know, people have been like fine-tuning stable diffusion and stuff like that, right? And they'll fine-tune stable diffusion to like, so that every result looks like Van Gogh. And then they show that you can interpolate between the original stable diffusion and your Van Gogh stable diffusion. So somewhere in that same convex basin, you had original stable diffusion and purely Van Gogh. So I think it's feasible that you can have some units, you know, you can have a unit in the basin, you can have an element over here that doesn't share some particular unit, but yet you can interpolate between them and get something that's reasonable. That's a great question. I know, yeah.
This might be fiddling a little bit. I'm not sure, or if it just doesn't come up in practice. But are there cases where you can have symmetries that are not layer-wise respected? So like if you have scaling or something, and so you have one layer that's like half and then one layer that's double, then when you compose them, it will be like the same thing. But then if you just go layer by layer, matching them won't make sense. Is that reasonable thing to question? Yes,
absolutely. It's a totally reasonable thing to say, and my answer is I didn't try it. Like I didn't do it. Okay. And the reason is partly because like there's a bunch of different types of symmetries here. One is like you could rescale. Another is you can sort of you can actually move things between layers, right? So I could have a feature. I might have a feature in layer 3, and you might have a feature in layer 5, and we can actually make that work, right? Especially in a ResNet. A ResNet's really easy. I could just have some blocks that are just totally no ops.
Yeah.
So there's a lot of ways to break this. And I think what's really interesting is like, why doesn't that happen? And also maybe you could do even better if you did do that. So like, I don't want to say it's not true. Rescaling in particular, SUD is kind of implicitly biased to have everything be of the same norm, right? So like, that's, you can kind of hand wave and say that. But like, yeah, like there's no reason not to do it. It's just that I didn't, because it's just adds complexity, but it would be a great thing to try. Yeah.
Okay, so there's no reason other than in practice, the same layer seems to learn about the same stuff, so you can match them up instead of like if I made a adversarial net for you and just stacked some no-ops at the beginning, then everything would die.
Yes, and in fact, we have this in the paper. We actually have kind of like a proof counterexample type thing of like constructing two models that you can embed into larger models such that no possible permutation of weights actually produces something. So in these things do exist in weight space. For some reason, SGD doesn't seem to pick them. And I think that's like a really interesting question. Another fun thing is, it's okay, we don't need a marker. Oh, perfect. Thank you. Like if you plot, you know, layer 1, layer 2, layer n, and then you train the same model multiple times and you look at the norms of the weights in each layer. Something that I found really interesting is like, they're all the same, like, but between layers, they change. So like, you know, your last layers maybe have a lot. It seems as though there's something like, they kind of die off in the middle as far as I can see, for some reason. But if you train multiple times, you get the same one. So like,
That's weird.
right, it is weird, right? Something fun there.
It's the same architecture, right? Just
Same, yes, sorry, that's an important question.
So I was wondering, maybe this will explain this later, but if you have ways of doing this for when permutations differ, like grouping in some ways, or I'm not really sure how you would even begin doing that, but that seems like it would be important down the line.
Yeah, I don't have an answer for that. I agree it would be important and good. But I don't have a solution for it. That's I think you have to get a little bit more clever at that point. I mean, it brings new complexities.
Somebody's asking, maybe I missed this earlier, what's the value returned by pi theta b?
What is the value? Okay, yes. So pi theta b, I guess I won't draw on the whiteboard since folks on Zoom probably can't see that. But pi theta b is going to be it's going to be weights for your model. So it's going to be the same shape as your input weights, theta b, but it's going to just move weights around. So it's going to be applying these permutation matrices. In fact, it's going to look exactly like this here. This P2, W2, P1. Once I've picked my pi is equal to just the set of all these p's. Once I've picked what those permutations are, I can just apply, I can just multiply through and it'll permute the weights and columns just the way I need them. And then the output will be a new set of weights with that permutation.
have you considered training on different data sets?
Yes, that's a great segue, and I will get back to that. Yeah. Okay. So it is NP hard, but I've never let that stop a good time. So here's a really simple algorithm. It's kind of dumb, but it works. Pick a random PI. So pick a random layer, in other words, freeze every other permutation and solve just that one layer. If you do that, if you freeze everything else, then it reduces to another linear assignment problem. You can solve that fast, put that back in the basket, and then repeat until you converge. And we also prove that you will converge. Do you converge to something good? No, probably not, right? I mean, in a theoretical sense, it's NP hard. So it's strongly NP hard, it's hard to approximate. We also prove that there's no like polytime constant factor approximation scheme. So, take all this with a grain of salt, but it's an algorithm and it seems to do something. Okay, and then finally, for sort of the most complex, but also slowest, we're all in deep learning, right? So maybe let's just learn the permutations or for some definition of learn. So let's try phrasing this as a optimization problem that we can move somehow. So how about this? let's try learning a new theta b. I'm going to call this theta b tilde. This has exactly the same shape and size as the original theta b weights. And then let's just try to minimize the loss at the midpoint between the two models. So this is going to represent a dense approximation of where, if we go back to this picture of the circle of all the different theta b's, maybe this is the original theta b, and then this is a pi theta b, and then I'm going to have some dense thing that I can just move around anywhere in the space that I'm calling pi tilde. And then at each step, we're going to project this. So we'll take this here and we'll project it to the closest one. And that's what this proj operator is doing. I'll move this over for the it's on Zoom. And this proj operator is just going to take the closest one, right? But okay, here's a nice thing. This optimization problem is actually the same thing as the weight matching algorithm. So you can run the weight matching algorithm in the inner loop. Okay, but a hiccup here. The projection operator is non-differentiable. Right, so what are we going to do about that? And in this particular case, we chose to use a straight-through estimator. So if you're not familiar with straight-through estimators, it's one of the few things that seems to work in deep learning. It's very simple. And all you have to do is in the forward pass, do the projection. In the backwards pass, don't do the projection. That's all it is, right? That's all straight-through estimators do. But it seems to work. It seems to work well in quantization and all these things. And so that is the straight-through estimator. Any questions before? Yeah.
How smooth is this? Because this might be a naive question, but I would just wonder if before you project it, like the loss, like I guess these are weights, right? So
Right.
like imagine I had a point that wasn't one of the points on the circle that was, what if the loss on that comparing to the loss when you project it is completely different? Like how do you know? I don't know how to phrase it better than that, but I hope you get what I'm trying to ask.
Yeah, like if I understand you correctly, I could be somewhere way over here, and maybe the loss here is 1,000,
Right.
and the loss here is like 100 or 10 million, or it could be something totally different. Is that?
Yeah, exactly. Once you get back to the point, basically, I'm just saying, like, what if that's non-trivial? Like, what if that jump isn't as small as you think it is?
Well, then
But
that's
it works, I
bad
guess.
news.
I'm just wondering if you checked, like, or if that, how that works into your argument, I guess.
Yeah, I mean, this is a kind of an issue with all straight-through estimators, that you can drift from your dense weights. In practice, it seems like it's not that much of an issue, but like it's a totally fair question. It's a totally valid thing. One nice aspect of this is that when you actually plot, your loss curve, that every value you get is an actual realizable loss value because you're projecting in the forward pass. So, some methods you have to worry about, is this actually a real loss? But you don't have to worry about that here.
I guess like it works. I've seen like straight-through estimator work in other places. I guess I wondered whether with weights specifically, given that the argument here is like, oh, it's convex, if that was something that you notice as a property here, because I'd sort of previously thought that maybe I'm not sure if that makes sense, but I guess I was just wondering if this goes to your argument about how weights are convex, or the space is presumably. I mean, John, yeah.
Yeah, it seems to work, but it could be that there's something more interesting happening behind the scenes. Like that's possible. It's possible that it's veering away.
Yeah,
I'm not entirely sure. Yeah.
Can you say the proj operator?
Yeah. So the proj operator, the goal of the projection is to take any point in weight space, and I want to project it to the closest. So let's call these. Let's say these are all x's, and these are all the possible permutations of my theta b. So I train one of them, and then there's all these kind of duplicates. And the goal of the proj operator is to take any point in weight space and find the closest x that's associated with it. And just in terms of math, you can write this down either as the L2 or as the inner product. And it's the same thing, but you can just think what's the closest one.
In terms of your individual inspiration for this, because I mean, straight through is used for a ton of stuff, but was there a particular thing that made you think, oh, I'll use it here? Because it really makes me think of VQPA personally, but I'm not sure if that's my individual bias.
Interesting. No, it wasn't VQPAE for me. It was it was a few different things. I mean, I've been thinking about the straight through estimator. I was thinking about doing Gumball softmax or something like that.
Yeah.
It's like it's too much work.
Yeah.
And this guy Aditya Kusapati, he just wouldn't shut up about the straight through estimator, and so I was like, fine, I'll try it. And try to bunch of different variations on it, stuff like that.
Yeah. Cool.
He's a big fan. The whole vision lab over there is a big fan of straight through estimator. And they're like, don't mess with other stuff. So I was like, all right, fine, I'll try it. Him and Mitchell. Mitchell is also a big component of this. Yeah. So at some point I gave in. So, all right.
I'll try it.
This is great. Yeah. Any other questions before I? All right. So I'll just say a quick thing. This is actually appendix material, but I think it's kind of cute. So I just want to throw it in here just in case. So let's say you want to merge more than two models. What do? Right? Because right now I'm only talking about two models at a time. Here's a simple algorithm. You have a whole batch of models. At every step, pick a random model out, average the rest of the crowd, and try to move your model that you pulled out to the center of the crowd. And you just do this, eventually you converge, right? Eventually you're going to iterate. And it's just like if every person in the crowd is trying to walk towards the center of the crowd, eventually sometime, you'll hit somewhere where everyone's kind of close together.
But if you have all the models like this, then won't the average be somewhere very far away from where any of the individual models are?
In the beginning, yes, but eventually it sorts out. So, yeah, this is doing, in particular, I usually do weight matching here. Straight through estimator is too slow for this. But if you do weight matching, you just sort of hop as close as possible. And like, if everyone is, you start out here, maybe, and then like the average is here, and then people go over to this side, and it sort of ends up, in this case, L2 is, or sorry, inner product is maybe not the right way to think about it. L2 is maybe an easier intuition of like moving towards, and they're equivalent, right, in this sense. Yeah, good question. Okay, so before I hop into experiments, let's see how we're doing with our collab. Hopefully we're done. Okay, and we are. So we have 3 models now trained with your 3 random seeds. And let's see what we got. Okay, so here are train losses and accuracies. Great, looks like we're working. Mia won. And when it comes to test loss, it looks like Bazil came out ahead, but it's close second. Sorry, Sachet, but yes, your model, I don't know. Okay, great. So we have our models. Let's try and interpolate between them. So here, I'll just show, this is interpolating between each of your 3 models as they are currently in weight space. So here's Mia to Sachet, here's Sachet to Bazil, and here's Mia to Bazil, right? Okay, great. And now let's try applying Git ReBasin. So in this particular case, I'm running the weight matching algorithm. It's the fastest and seems to work well. And I won't belabor sort of the code for you entirely, but I will just point out it's not, this is all it is, right? So maybe 50 lines of code, something like that. And it's doing exactly what I told you. So we just pull out random P, and then we permute it as best as possible, or sorry, we add up the other parameters, we do a linear sum assignment, and then move forward. And then we just keep doing that until convergence. So nothing hid under the rug. So now, okay, let's try matching our models. So first I'll match, I think this is Mia and Sachet, A and B. And so, this will just take a second. And then, and also I'm showing here at every step, what's our improvement in terms of our inner product. Until finally we're done. So that took 13 seconds. So, and I'm also showing here, we started with an L2 distance of 128, and it went down to 110. So a small improvement, something. But then the inner product really goes crazy. So you can see here we have over 1,000% increase in our inner product between the two models. Okay, and then I'll just run the other two. These run pretty fast, especially when you're on a good GPU. Okay. Oh, I didn't do the drum roll, but now, after we've done the permutations, this is the same plot. So now we've taken what was this very non-convex thing with a big bump in the middle. I've moved you to a closer point in weight space, and suddenly it's starting to look convex. Right? So the argument here is that there's nothing special about the seeds that you chose in particular. You could have picked anything. And we're starting with something that was non-convex. We convert it into something that is convex. Therefore, ultimately, you all were in the same basin, just in different permutations of that basin. All right. So now let's try merging multiple models. So this is also that algorithm I just presented. And again, it's exactly as I said, we pull a random one out, we do weight matching, we take all the other models, and then we apply it. So let's try that, and I'll merge all of your models together. And then while that's cooking, let's hop back to these experiments. So, okay, great. So we ran this on a bunch of different models, a bunch of different data sets. So here I'm just showing an MNIST MLP. This is like what we're running in the collab as well. And in this case, we can see that all the methods seem to do decently well. Interestingly, activation matching was not quite as strong as the other two. And also surprising to me was that the straight-through estimator didn't really bias anything more than weight matching was already able to accomplish. So not entirely up to my expectations, but again, it's MNIST and it's MLP, so take all that with a grain of salt.
At the same point, they all start at the same point. I think model A and model B, all the curves would convert at the same point from that, right?
Model A and model B. Oh, on the right here.
Yeah,
Like, why is there a smidge of green?
or why, maybe I'm misconstruing the plot, but I would think that if you're all the land is 0, you're at model A.
Yes,
It should always be just model A.
that's right.
It's gonna be, but then for model A, there's actually two.
Oh,
There's multiple curves that it's not all the same point, basically. All the curves are not converging at the same point there.
great question. And this is something I should clarify. Yes, the dashed lines here are showing test loss, and the solid lines are showing train loss. And it's a little bit, it's a little bit confusing viewing it from this angle and the side.
I said getting that. Yeah, okay.
No. This is my fault, and I should make better plots. This is a lesson for, yeah. I mean, so down here, this is showing train loss, and this is showing test loss.
Okay.
Yes,
So they all are
yes,
at the same point. Okay.
yes. Great question. That's yes.
Yeah.
So I guess the interpolation only happens in test loss, so you don't have a train loss. Or there is.
You get basically the same effect in train loss, so it goes totally flat. But the thing is, in train loss, you're going down to 0 anyways, and so you're not going to be able to go lower than 0.
But if you interpolate to unmatched models, in train loss,
Yeah.
does it have similar trends?
Yes, and this is where the plot gets confusing,
Okay,
but that's this
that
line
makes
right
sense.
here.
I see. Yes. But the trend is basically like it's exactly the same as test loss. I would expect from like difference at the peak maybe.
Yeah, it's kind of an interesting thing that once you do the naive thing and you do in the middle, it's just totally garbage. It's effectively a random initialization.
I see.
Which is kind of an interesting phenomenon. But yeah, I agree. It seems kind of odd, right?
Right.
Yeah. Yeah, good question. Yeah.
It's not any more garbage on test than on train at that point.
Yeah. Like at that point, the argument is like,
Yeah.
this,
That
you know.
point should just do it anyway, so it's all the same.
Right. So here, yeah, here's a case where we're doing CIFAR-10. We're using an intentionally sort of underpowered MLP model so that we can run all of our methods. And here you can see a similar story. So we're not able to get perfect connectivity here, but it is an interesting case where we see that there is a benefit to straight through estimator over just doing weight matching here. And then CIFAR-10 is not out of reach though. So here's CIFAR-10, but with a ResNet model. And we can see that we actually achieve perfect linear mode connectivity. And this is one of our sort of headline results. This is, to my knowledge, the first such demonstration. And then finally for ImageNet, we also applied a ResNet 50. Notably, in this case, we had to increase the width quite a bit. Here we're doing ImageNet with the standard ResNet 50. And this is actually using off-the-shelf weights from a model trained by someone else that we downloaded off of the internet. We trained our own model and did it. So there's no futzing around of like, we actually took someone else's model and applied it. And this is a case where, yeah, we're not seeing perfect connectivity, but we hypothesize that again, if you bump up the width, we could get that down.
What does higher width mean? Better.
Great question. That's also a good segue. Or it's a segue for 2 slides from now. But another thing, there's a few interesting things to sort of interrogate here. One is that this linear mode connectivity appears to be an emergent property of training. So if here I'm plotting every epoch and I'm plotting that barrier, so how big the bump is for 2 models, I'm training 2 models, I take the weights of every epoch, and then I'm going to plot that. And we see that it's sort of this thing that happens gradually over the course of training. So in the beginning, there doesn't seem to be good connectivity at all. It's not entirely clear why, but then over time you train and suddenly you can connect. And then you can see a similar story when it comes to CIFAR-10. Yeah, and this is just a blow up of like those plots we saw before of the interpolations. You can see we're going to convexity. And then you can see a similar story for CIFAR-10, but it's just a bit noisier since it's a weaker model and a larger data set, but kind of a similar thing. One interesting thing to point out here is that it's kind of a shortcoming of the loss barrier metric. Here you can see that we're actually interpolating everything in between is kind of below this, interpolation of the losses, but still we have positive barrier. And this is a subtlety of how the actual metric is defined. It actually can't go negative. So 0 is the best you can get, and you're kind of stuck in these situations getting positive. Oh, another thing I'd like to add is a really cool result after we put out the paper. Someone else came along a week later, and from Frederick Benzing and a few others, and they actually managed to get this down to 0. And it's very neat. But what they do, if I understand them correctly, is that they are training, they're taking the permutation here, and then they backport that to the beginning and apply that there. So if you allow yourself to look into the future, you can backport a permutation and actually get that down to 0. Yeah, that's Benzing et al. 2022. So also a very cool result. Okay, and then to get to the question of width. Yeah, there's a strong association with width, and it's not entirely clear why. There's a few hypotheses, but we get to understand more. So here I'm taking, this is a VGG model trained on CIFAR-10 for various widths. So this is the standard model, and then we increase it and decrease it. And this is showing the barrier. And it's a very clear sort of trend here. As we get more and more width, we do better. 8x width you can't fit on a V100, so it did not happen, unfortunately. But just kind of, hopefully we can get some new GPUs at some point. Yeah, and we can do a similar thing with ResNet 20s. And so here we can sort of increase the width, and here we can actually go all the way down to 0. So both in test and in train, we're going all the way down.
Do you have like a hand wavy justification to yourself? Like it seems like, well, if you have more width, maybe you have only so many things you can learn in this layer, and you learn the same ones in different models. And also, if you have more width, you have more degrees of freedom to play with in permutation, or like any of those what is your personal favorite hand wave justification?
It's a great question, and I don't. Yeah, I'll say some things. We're veering now off of things that I can say definitively to be true, but we're heading into belief space.
Yeah.
But one argument is like, okay, you just have more things to match, right? And so if you think about just like optimal transport or matching, right? The more things you have to match, the easier it is to match them. And it's scales like, I don't know, I think it's like big O n to the negative d or something, right? So it's actually quite nice that it goes down quite a bit. But another thing is, I think you're probably learning different types of features in different models. So my favorite hypothesis here is that when none of us are training models that are actually wide enough, right? Like actually, if you had as many features as you wanted, you could put every possible thing. You could put, you could have a unit for dog, and you could have a unit for, chair with ruffles, and you could have a unit for jacket. And if you have enough of these, then the element-wise nature of your activations kind of implicitly biases each unit to capture a single concept, kind of monosemanticity. And then I can match them more easily. And in these smaller models, I'm kind of like just sort of Johnson-Lindenstrassing down. I'm just randomly projecting down the activations at each layer. This is a hypothesis. So your loss metrics look similar at the end of the day, but what's happening mechanistically in the model is different. And if you have random projections, there's no way I can permute those. I have to do some kind of rotation, and then that gets more complicated. There's a great paper from Anthropic. It's like a paper blog post type of thing that talks about some similar ideas. So that's my favorite hypothesis, but it would be really cool to understand better why that is, like on a deeper level, because that's very hand wavy, right? Yeah, great question. Yeah.
This could be a ridiculous question because I don't know much about that sort of related, but so you sort of define method to find sort of you're interpolating two models, right? So it's like a line in the high-dimensional space, like the weights, right? And you can reasonably find like two lines in space. So I guess my question is it possible to interpolate these two lines? So you define like an area.
Oh, so
Convex shallow permutation.
And then you can do like,
yeah, it's a good question. People have done this.
right.
Not with permutations per se, but people have done like learning a whole simplex all at once.
Right.
Yeah, and it works. I think Andrew Wilson's group has something on this actually. He's in New York. I know his group. They've done a lot of great work on like the geometry of loss landscapes. So they've done things on like they've previously shown that all points are like form connected volumes, and like this mode connectivity stuff, nonlinear mode connectivity stuff comes from their lab. And then there's also, I know Mitchell Wordsman had a paper about this. But yeah, it can be done, and maybe doing that with permutation would be cool too. All right. And then, yeah, just to confirm, it is flat. Okay, so this is getting back to a question from before. You asked, okay, what if I have different data sets, right? So, okay, let's try that. So here's an experiment. We took CIFAR-100, and we built two data sets. One is biased towards labels 0 through 50 against labels, 51 to 100. And data set B is the opposite, right? No data point is in both data set A and data set B. They're disjoint. We trained separate models on each of these two data sets, each data set being biased, and then we combine them. So the idea here is, like, let's say you're some large, conglomerate or something, and maybe you have user data in the US and you have user data in EU or something, and you can't combine the data because of GDPR or whatever, stuff like that. But maybe I could train separate models, and then I could actually combine them in some sort of symbiotic way, some sort of synergistic combination. And we showed that if you merge them, this is actually possible. So if you merge naively, you get something very bad. if you merge them with Git ReBasin, you actually can achieve models that are better than both of your input models on your combined space. So you're actually getting some positive outcome by merging it.
Sorry, I don't think I fully understood. How did
Yeah.
you train model A and model B?
So the only difference between model A and model B is that they're trained on the different data sets. So dataset A being biased in one way and dataset B being biased.
Okay, so just more labels, like more of those data points.
Yes, exactly. Yes. They're just biased to have more data points from one. Yeah.
Do they have the same task and the same classes, categories at the end? Because otherwise you'd have to start reading or something like that as well. That makes sense.
Yes, they all have the same labels,
Okay, okay, yeah.
output space. Yeah.
Just like half of an image heads and another half of image heads or something like that.
Yes, and then they're just biased towards which
I
categories.
see, I see.
Good question. And yeah, I mean, maybe you could do something where you have totally separate things. I'm not sure if that would work, but
Can you do it like can you be selective about which layers you want to fuse and somehow pick permutations around a particular neighborhood of layers and say, okay, at the end, these networks will go different ways, but the features I need up to here should be basically the same thing. So I want to fuse basically the
Like-
common head that I think should be shared
I see.
between these, and then leave the rest alone. That would also let you do this like multitask different label spaces kind of thing, but I don't know if it would work or if you need all the permutations all the way through to be able to.
No, yeah, you can totally do that. Yeah, you don't actually need, for the straight through estimator, it'd be tricky, but for like activation matching and weight matching, you could totally do that. Absolutely, yeah.
What do you think would happen if you did different modalities, like for example, classification of, and you know, and you use a spectrogram image?
I don't know. I think it's gonna be worse. But then the question is how much worse? I'm not sure. Yeah. I think that hopefully, as long as you have some commonality between your tasks, you're gonna have features that might overlap and then you can do something. But the further away your distributions are, the harder it becomes, right? So just naturally, it's a more challenging task.
This is very cool.
Oh, thank you. Thank you. Yeah, I appreciate it. And you know, notably, we're not beating ensembling, but ensembling has twice as many parameters in compute. And we're not beating full data training, but that's cheating, so you can't do that. Yeah.
Have you looked into like fairness with if we did it this way versus?
Great question. I haven't, but like, yeah, here's something I think would be really cool to try. Is like, could you gerrymander data this way? Like, you could envision that there's bad outcomes here. Of like, I could take all my data, and if I split up, if I, you know, let's say I want to say I don't like, you know, some group of people, or I don't want to do this or that, I can just take their data and maybe I put it in certain slots such that it just washes out in this average. It seems feasible, right? It seems, I don't know. Luckily, no one's doing this, right? In reality. But yeah, I don't know, it's a good question. And people are doing federated learning. So like federated learning, it's very real. That's something to worry about. Yeah. Yeah.
So this is kind of a high level question. So if you were to continue this line of research for the future,
Yeah.
do you think it's more important? Like, do you think that one interesting question is how do you combine weights to get better performance, or just interpretation of neural networks in general?
I mean, I think, you know, this may be cliche, but the best research directions are the one that, you know, you want to do. Like,
Right.
so, but I think my experience with this project has been like, I was interested in the geometry of lost landscapes, and I first wrote the paper in that direction. I then got feedback from friends of mine who said they could not care less, and they said that what people really care about is what they can do with it, and like, so concentrate on the merging models thing, and so that brought out no experience. So like, I mean, you know, it was good because it was a very eye-opening bit of advice, and I think it improved the paper quite a bit. But it's a different angle. Yeah. And I think there's interesting things in both directions. So don't let it stop.
You have one for you, one.
Yeah, it's like, right? And it's interesting too, because like, it's the same code, it's the same algorithms, like it's the same basic writing of the paper, but you change the abstract, you change the title a little bit, and then suddenly people care. And like, and that was kind of eye-opening.
Marketing team comes in.
I know, dude, I really have to give a shout out to my friend Ophir. He read this and he was like, this is just the most horrible, like change everything. And so I moved things around and I focused on the merging thing. Yeah. He comes through once in a while. So this is I'll just say this quickly, it's a fun result that I'm partial to, but didn't make it as the main paper. So you might ask, okay, what effect does this have on the calibration of our models? So on the x-axis here, I'm plotting the probability that comes out of the model. On the y-axis, I'm plotting the true probability. What do I mean? I mean, if your model predicts that something is a cow with probability 17%, then 17% of the time you predict that, it should actually be a cow, right? So you can look at all of your labels, you can look at all of your predictions, and you can batch them, and then you can plot this curve. And ideal performance is going to be a straight line, right? So 0 probability, 0 probability, 1 probability, 1 probability, and everything lines up perfectly. And so this is the result. So this is showing two CIFAR-100 models. If you just naively, these are the models themselves, model A and model B, in the colored lines. And then if you just naively merge them, it can get worse. And then we show that if you do this Git ReBasin merging, suddenly you get near perfect calibration. And this is showing for that bias data experiment from before. And we see a similar story in terms of test performance, but obviously test is harder. Okay, and then before I do this, I want to try hopping back over, since this is where we left off here, and see if it's done. Okay, all right, so we've merged all the models now. Let's see how we did. So I took all three of your models, I ran that algorithm, pull one out, merge, pull one out, and now let's average the results and see how we're doing. Let's run this. And you can see that our input models had test loss around, let's see, 0.14, 0.5, 0.14, and then our combined model has 0.09. So we actually decreased our test loss by 37%. There's a slight penalty to accuracy, but it's quite narrow. So you can actually get some benefit if your goal is just to get state-of-the-art numbers on some data set. This may be a way to.
And that's better than just if you were to run all three models independently and average towards the end, or
If you do ensembling, I don't know if you can do better than this. Ensembling is really. And ensembling, if you can do ensembling, you should totally do that. Absolutely. Yeah, absolutely.
That's a question that
Yeah.
will seem very naive, but why do we care that test loss is lower if test accuracy isn't that much better than if it's not?
Like why bother?
Why specifically loss versus accuracy, right? Because I usually don't really care about my loss, I only care about my accuracy, right?
Sure. I would say that yeah, maybe you don't care, and maybe that's, maybe this isn't.
No, that's fine.
No, that's fine. You.
No.
Accuracy is basically saturated here anyway, right? So
Yeah.
the difference of this is like 1, and they're all basically.
So is that the case? Like, I guess not, because we saw other results, but I guess I was just trying to point out, like, I don't know why loss is particularly.
I think yeah, I don't think that, like, not everyone cares about loss, and I think that's okay. I would say as a field, I think that we care about loss maybe not as much as we should. Like in particular coming from, like, I'm currently employed by an autonomous vehicle sort of company, and like you could envision that they might care more about robustness and calibration than top line
Right.
like top one performance. But everyone has their own needs, right? So I hypothesize that what's happening here is that we're getting a little bit better calibration and therefore less confident. And so that means your top one accuracy may be going down, but your loss is improving. But it's a great question.
I feel
Yeah.
like accuracy is just one dimension to evaluate. Like it's evaluated on the classification loss, whatever. But there's other metrics you can evaluate this model as well, in which case it could do better. Also, I feel like from an optimization standpoint, the test loss represents how well the model is trained for this specific object. So I think if you're studying like optimization problem instead of trying to solve the classification problem, then you should. So it makes sense.
Yeah.
For regression task is actually the same thing.
That's a fair point. Yeah, I hadn't thought of that. Yeah. Sure.
Can you go to the slide?
Yes.
Calibration. That's like pretty amazing, right? It's like, that's a huge research area, like figuring out how to calibrate models well. So is this the case even if you had trained two models on the same data set, not just bias data, would it still be better calibrated if you did this interpolation?
I hope so. Yeah. I don't know if I have that exact experiment. I actually I ran this experiment 2 hours before the iClear deadline. So but I do have one thing I can show you. I'll use this as a segue to hop forward in the slides a few. This is what we saw previously, except 5 models instead of 3, and you can see we get a nice improvement in test loss. Here's an example where actually I trained 32 different models, and each model sees a random 50% of the same distribution. I believe it's MNIST in this case, and but it's the same distribution, uniform random 50%, and then we can see a similar story. That's not exactly answering your question totally, and yeah, it's a good question to try. It'd be nice to see that kind of result. Yeah. And here's a case where naive just kind of, you know, falls off a cliff. It's a great question. Here's my intuition, but I'm not sure if it's right. Let's envision the loss landscape. Let's say this is the test loss. Your train loss is going to be slightly perturbed, but it's going to be similar, right? It's going to be like something like this. And then I converge on train loss, I converge to something that's zero train loss. But I'm not hitting exact 0 test loss because there's always some shift. But if I do this a bunch of different times, first of all, the basins are actually very flat. So when you have wide models, you have very flat basins. So you know, flatten that. It's like this. So I may train here and you may train here. And if we average, we do a lot better in terms of finding that center. And I think if you do this with a bunch of different train loss, test loss distributions, then you sort of end up averaging things, and averaging things in a convex function is always a good idea. Yeah. That's my intuition. Not a solid confirmed experimental finding, but yeah, great question. And so finally, I'll just say a few words, some parting thoughts. So number one, it seems as though loss landscapes, at least certain loss landscapes, especially in vision, contain only a single basin modulo permutation symmetries. Wider models are better. And I think the question is, to what extent will this generalize to more architectures, more data sets? I've heard from people in NLP that they think that there's no way this is true in NLP. It could be, I have no idea. Certainly different problems have different kind of constraints. Number two, just as a practical note, this is a tool. It's kind of a hammer that maybe if you ever come across sometime, you need to merge 2 models together. This is something you can kind of pull out of the tool belt, and it seems to work decently well. And oops, number 3, these merge models actually seem to be better calibrated than the inputs. And so maybe there's a methodology here for improving performance, especially in these cases where you can't share data. Maybe you're doing federated learning, maybe privacy sensitive learning, something else. And so with that, I'd like to say, and I have a slide of some different future work and stuff like that. We can happy to talk about that as well. So I'd like to thank my great collaborators. This work was also done with Jonathan and Sid. Jonathan was a absolutely fantastic and also should be mentioned here as well. And with that, I'd like to say thank you so much. Thank you, Carl, for having me in your space and inviting me. And it's an honor to be here. And thank you all for all the great questions. So yeah.
Amazing talk.
We probably have time for like 1 or 2 questions. And then we push the one-on-ones. Anyone has any questions on Zoom, feel free to ask them. Sam, are you, is your volume on? Yeah.
Yeah.
Yes.
Yeah, us 3 things.
No, that's your.
Oh, that's right.
Anyone here have any questions?
Sure.
So I guess in the paper you studied small models. Is there any plans to?
What's next? Bigger models.
Right.
Yeah. So the biggest model that we ran was the ResNet 50s. But that's, rapidly ResNet 50s are becoming small models. Even since, I put out the paper now, it's yeah, I want to run this on like vision transformers and stuff like that. We did try, we tried running it on conv-next models. But they have this interesting property where there's actually way fewer symmetries there than you'd expect. So they do this thing where they do, I forget what they call it, depth-wise convolutions. Like they do convolutions the wrong way. And then it becomes, it depends, like the order of your filters matters. And so then you can't permute things, and like so that's a pain. Vision transformers and transformers in general, that's something we can do. You do have to worry about if you have multiple attention heads, you have to be able to swap things between attention heads, but we think we have a way to do that. But yeah, I would like to. Yeah, this is obviously, just sort of first steps. Yeah.
Giving this might work for recommendation models. So say your dataset A of user item interaction in your feature vectors for each user each item. Dataset B from say your same stuff, and then you merge to a network that just takes the user item user vector item vector deep network, optimizes the losses to the embeddings, then take the 2 networks and merge them. Something I guess I feel like would be very important to industry. But I'm curious if someone's tried this or whether you think it'll work.
No one has tried exactly that to my knowledge. But yeah, it would be very interesting to try. I think I'm not entirely sure what people in industry are doing and what they're up to these days. But I would like to hope it would work. Yeah.
Yeah, as a follow-up to that, you said there's something about vision, and then you said people in NLP believe this might. What is it about vision data sets?
Well, I mean, I don't actually think there's anything super special about vision, to be honest. I think NLP people like to feel special. And but they also have there's some legitimacy here. So like, some of these NLP models will plateau for a while and they'll have like kind of grokking type of behavior, which to my knowledge is not as prevalent in vision. Perhaps, I mean, all of you would know better than I. But, I think all these things are basically the same. We just haven't figured out the right language and we don't have the right system to connect everything yet. Like, I don't think that vision and language are like too fundamentally like, they're just slightly different problems. They have slightly different constraints and people use different optimizers, different things. Under the right lens, I'm hoping that we'll have a consistent picture.
And
Like,
the last question is
yeah.
the loss function. So I'm assuming simply like I'm assuming you use cross entropy broadly. What about other loss functions, say like compressive loss or? Yeah, I guess, anything else we tried that, or is there something special with cross entropy that requires it for this to work?
Not to my knowledge. Cross entropy was used for all these things because they're sort of, the standard off the shelf classification problems, but absolutely, yeah. I have not tried it. It would be fun to see. I am hopeful that it would work. I don't know of any reason why doing cross entropy is special.